For years, astronomers know that nearly half of the universe's ordinary matter seems to be missing. It is not dark matter and it is not gone. It is simply too thin, too hot, and too invisible to see directly. Then fast radio bursts, tiny flashes from across deep space, begin to expose what telescopes cannot easily find. In this video, the story follows how these brief signals help reveal the hidden matter between galaxies. If this kind of cosmic mystery is interesting, please like the video and subscribe to the channel. At the widest scale, the universe presents itself as a ledger of contents rather than a collection of familiar objects. Galaxies, stars, planets, gas, dust, and the thin light that crosses immense distances all belong to one broad inventory. But that inventory does not add up in the way human sight once suggests. Modern cosmology describes a cosmos in which ordinary matter, the matter built from atoms, forms only a small share of the total cosmic budget. The rest belongs to dark matter and dark energy, two dominant components that shape the large structure and expansion of the universe while remaining unlike the matter of bodies, stones, air, water, and stars. Measurements of the cosmic microwave background and other cosmological tests converge on the same broad picture. Only about 1/20th of the universe is ordinary matter, while dark matter supplies a much larger share of matter, and dark energy supplies the largest share of all. In this broad accounting, the first important distinction becomes clear. The missing matter problem in this story does not refer to dark matter. It refers to ordinary matter that theory says should exist, but that observers for many years do not fully find. This ordinary matter is often called baryonic matter. A baryon is a particle such as a proton or a neutron, and baryonic matter is the common material from which atoms are built. Electrons complete atoms, chemistry begins, and everything visible in the daily world follows. When cosmologists estimate how much of this matter the universe should contain, they do not begin with nearby galaxies alone. They use evidence from the early universe, especially the relic radiation left from the hot beginning, together with the well-tested physics of primordial element formation. These methods do not depend on counting every star or cloud one by one in the present era. Instead, they establish a cosmic allowance for ordinary matter long before galaxies mature into their modern forms. That allowance remains remarkably stable across many studies. It implies that ordinary matter exists in a definite total amount even when much of it is too faint, too hot, too thin, or too spread out to register easily in ordinary surveys. The puzzle therefore emerges from a mismatch between prediction and inventory. The theory of the cosmos says the matter is there. Telescopes, for a long time, recover only part of it. The scale of the mismatch becomes clearer when the idea is stated carefully. Ordinary matter makes up only a small fraction of the total contents of the universe. Yet even within that modest fraction, astronomers struggle to complete the count. The problem therefore sits inside a larger imbalance. Most of the cosmos is already not ordinary matter at all, and then even the ordinary portion seems only partly visible. This gives the subject an appearance of layered absence. One absence concerns dark matter, whose nature remains unknown. The other concerns familiar matter, whose nature is already known, but whose location is not fully charted. Keeping those two absences separate is essential, because they arise from different evidence and lead to different scientific questions. For decades, astronomers build this inventory from what shines brightly and what absorbs light strongly enough to stand out. Stars offer the clearest contribution. Galaxies full of stars can be counted. Cold gas inside galaxies can be traced in several ways. Hot gas in clusters can glow in energetic light. dust can be inferred from the way it dims and reddens more distant sources. These methods gradually assemble a census of ordinary matter in the nearby universe, but the total keeps coming up short. The shortfall is not tiny. In the local cosmos, roughly half of the expected ordinary matter remains unaccounted for in direct observations for many years. This does not mean half of all matter in the universe is missing. It means that a large fraction of the small ordinary matter share is not turning up where observation most easily looks. The distinction matters. Dark matter remains a separate problem with separate evidence. The missing baryon problem concerns matter that is entirely ordinary in its particle nature but elusive in its distribution and physical state. It is missing from the books of observation, not from the laws of physics. That difference between kinds of cosmic absence shapes the whole subject. Dark matter announces itself through gravity. It bends the motion of galaxies, helps bind galaxy clusters, and provides much of the gravitational framework within which ordinary matter gathers. It is called dark because it does not emit, absorb, or scatter light in the familiar ways required for direct viewing. The missing ordinary matter of this story behaves differently. It is not exotic. It is not a new ingredient added to the cosmic recipe. It consists of the same basic material that forms stars and gas clouds and living bodies. The problem lies in where it resides and what condition it occupies. Matter that is very diffuse can evade emission-based searches. Matter that is highly ionized can become difficult to detect in traditional optical surveys. Matter spread through enormous volumes can contain substantial total mass, while remaining almost invisible at any one location. In this sense, the universe can hide common matter in plain sight, not by changing its identity, but by thinning it out across distances so large that brightness falls beneath easy detection. So the opening view of this subject remains calm but unsettling. The universe is not failing to contain its expected atoms. Observations indicate that the atoms, or the protons and neutrons that would form them, exist in the expected total amount. The difficulty lies in performing a complete census across a cosmos whose ordinary matter does not remain neatly packed into luminous islands. The grand total is known from early universe physics and later cosmological measurement. The local tally, for a long time, is incomplete. Between those two facts sits one of modern astronomy's persistent bookkeeping problems. The missing share belongs neither to fantasy nor to speculation beyond established physics. It belongs to ordinary matter distributed in ways that frustrate direct counting. At the widest scale, then, this story begins not with an explosion, a galaxy, or a single signal, but with an imbalance between what the universe says it contains and what observers can comfortably place on the page. Once the cosmic budget is separated into ordinary matter, and dark energy, the next step is to ask where the ordinary share actually resides in the modern universe. The eye is drawn first to galaxies because galaxies are where light gathers. Their stars define spirals, ellipses, bars, and bright central bulges. Their gas forms glowing nebulae, dark lanes, and broad disks. They appear to be the natural storehouses of ordinary matter because they are the places where matter becomes visible in familiar ways. Yet the cosmic census does not support that first impression. Galaxies are important concentrations of ordinary matter, but they do not hold most of it in forms that shine brightly. The visible parts of galaxies are only the densest and easiest to see parts of a much larger distribution. When astronomers add together stars, cold gas, dust, and other clearly observed components, they find that these luminous islands account for only a limited portion of the expected baryonic total. The search for missing ordinary matter therefore expands outward almost at once. It becomes less a story about bright objects alone, and more a story about everything that lies around them and between them. This shift in perspective matters because stars dominate attention far more than they dominate mass. A galaxy may look like a city of stars, but the stars are not the whole baryonic content of that system, and galaxies themselves are not the whole baryonic content of the cosmos. A substantial share of ordinary matter exists as gas rather than as stars, and much of that gas does not sit in the dense, cool forms that stand out easily in ordinary imaging. Some of it lies inside galaxies, mixed through their disks and central regions. Some of it extends well beyond the visible boundaries of starlight. Some of it occupies the far larger spaces that separate one galaxy from another. For a long time, the bright stellar component gives a misleading sense of completeness. It is easy to assume that where most of the light is found, most of the ordinary matter must also be found. The modern baryon census shows otherwise. Recent work using localized fast radio bursts supports a picture in which only a small remainder of ordinary matter is concentrated within galaxies themselves, while much larger fractions lie outside them, either in surrounding halos or in the intergalactic medium. This means the missing baryon problem is not primarily a problem of hidden stars. It is not solved by imagining large unseen populations of ordinary galaxies, nor by supposing that familiar galactic matter has somehow escaped ordinary astronomy only because it is dim. The deeper issue is that much of the baryonic mass occupies environments that are physically diffuse. Matter can be real, widespread, and substantial in total mass while remaining faint at every local point. A cloud that is very thin across an enormous volume can outweigh a compact bright structure without ever looking dramatic. This is one of the central difficulties of cosmic bookkeeping. Observation tends to favour what is dense, bright, cold, or sharply bounded. The universe does not arrange all of its ordinary matter in those convenient forms. Instead, it spreads much of that matter into tenuous gas, often highly ionized, so that the mass is real but the visibility is weak. In that condition, ordinary matter no longer resembles the compact scenes of stellar astronomy. It becomes part of a broader and quieter background of cosmic material. The idea that most ordinary matter lies outside bright galaxies therefore changes the geometry of the search. The relevant volume is no longer mainly the interior of galaxies. It is the much greater volume surrounding them. Even if that surrounding material is less dense by a large factor, the sheer extent of space involved allows it to dominate the baryonic census. Matter inside galaxies occupies relatively compact regions. Matter beyond them occupies the far broader domain of extended gas around galaxies and the immense intervals between them. Once the problem is framed in this way, the shortfall in the baryon count begins to look less surprising. Astronomers are not merely missing matter inside known structures. They're trying to trace matter distributed across regions where brightness is intrinsically low and where the signal from ordinary atoms becomes difficult to isolate. In this sense, the problem is not simply that matter is hidden. It is that the main reservoirs of ordinary matter are not arranged in the places where human observation first learns to look. The emerging census gives this picture numerical form. A major study announced in the middle of 2025 reports that about 76% of the universe's ordinary matter lies in the intergalactic medium, about 15% resides in galaxy halos, and the remainder is found within galaxies and stars or colder galactic gas. These values align with long-standing expectations from cosmological simulations. but the importance of the result lies in observational confirmation. They show that the dominant reservoir of ordinary matter is not the luminous body of galaxies. It is the thin material outside them. Galaxy halos also matter because they form a transitional store of gas that belongs neither to the bright stellar interior nor to the emptier stretches farther out. Together, the intergalactic medium and the gas around galaxies contain the great majority of ordinary matter. The phrase missing matter therefore refers less to matter absent from the universe than to matter absent from the bright, compact environments that once seemed the natural centres of the search. At this stage, the picture remains wide and simple. The universe contains the expected amount of ordinary matter, but only a minor share is packed into the stars and dense galactic material that dominate the visible scene. Most of it resides outside those bright structures. The missing baryon problem is therefore a problem of placement and state. Ordinary matter is present, but it is dispersed through a far larger realm than the realm of galaxies alone. The modern view replaces the old intuition of matter gathered mainly into bright systems with a calmer and more expansive one. Galaxies are not the full storehouses of ordinary matter. They are the luminous markers embedded within a much broader medium. Once that is understood, the search for the missing share stops being a hunt for hidden bright objects and becomes an effort to understand the quiet baryonic material that fills the vast spaces beyond starlight, beyond the bright outlines of galaxies. The universe arranges its ordinary matter within a much larger pattern. On the widest scales that can be mapped, matter does not lie down evenly like a smooth mist. It gathers into a vast framework often called the cosmic web. This name refers to the large-scale structure of the universe, a pattern of long filaments, dense junctions, surrounding halos, looser sheets, and broad underdense voids. Galaxies mark this pattern because they tend to form where matter is already concentrated. But the galaxies are not the framework by themselves. They are the visible knots and traces embedded within it. The larger structure includes far more than the luminous parts of galaxies. It includes the broad distribution of ordinary matter and dark matter together across distances so large that individual galaxies become small features within a continental-scale arrangement of cosmic terrain. In this view, the missing baryon problem begins to leave the boundaries of single galaxies almost entirely. The likely reservoir is not one hidden object or one overlooked class of star. It is the web-like architecture of the mature universe itself, spread across the spaces that connect galaxy systems to one another. This structure grows over cosmic time from tiny variations in density present in the early universe. Gravity gradually amplifies those small unevennesses. Matter flows towards slightly denser regions. Those regions become more pronounced, and the overall distribution evolves into a network rather than a uniform field. Dark matter plays the leading gravitational role in this growth, building the underlying scaffolding, while ordinary matter falls into the same broad pattern and responds to the same large-scale pull. The result is a cosmos in which clusters of galaxies sit at major intersections. Smaller groups line the filaments, and long bridges of matter stretch between dense nodes across immense reaches of space. Around galaxies and groups lie extended halos, reservoirs that reach far beyond visible starlight. Between the denser sites lie filaments that are not empty but are much harder to see directly. Beyond them lie voids, regions of much lower density where matter is sparse. The cosmic web is therefore not merely a decorative description. It is the main spatial arrangement within which the baryonic matter of the modern universe resides. When astronomers consider where the uncounted ordinary matter is most likely to be found, this web becomes the natural answer. The missing share is not expected to sit randomly through space. It should follow the gravitational geography of the large-scale structure. Matter tends to accumulate in and around the same framework that guides galaxy formation. Some of it remains inside galaxies, some of it surrounds them in extended halos, and a great deal of it occupies the filaments and diffuse regions connecting larger systems. This expectation arises both from theory and from numerical simulations, which show that a substantial portion of ordinary matter at later cosmic times should inhabit the broad web between galaxies rather than the dense interiors of luminous systems. In these models, the universe keeps most of its baryons in places that are gravitationally meaningful but visually subdued. The cosmic web therefore acts as a reservoir not because it is a single container, but because it is the dominant environment through which ordinary matter is distributed on large scales. The web also changes the meaning of distance. The space between galaxies is often imagined as a near-empty separation, but on cosmological scales it is better understood as structured territory. A path from one distant galaxy to another does not pass through simple emptiness. It crosses halos, filaments, outskirts of groups, and large domains of thin material arranged by the web. Even where the density is low, the cumulative amount of matter along vast distances can be significant. This is one reason the missing baryons remain so difficult to tally through ordinary imaging alone. Their principal environment is extended rather than compact. Their distribution follows corridors and envelopes rather than sharply bounded objects. A filament may contain a great mass of ordinary matter while remaining faint, because its material is spread across a gigantic volume. A halo may hold more baryonic mass than the visible stars of its galaxy suggest. Yet much of that mass may sit far from the stellar disk where brightness falls away. The cosmic web does not hide matter by placing it behind a curtain. It hides matter by stretching it thinly across the dominant architecture of the universe. This picture gives the modern cosmos a quieter appearance than the one first offered by starlight. Bright galaxies remain the signposts. But the real baryonic landscape extends well beyond what those signposts illuminate. Clusters of galaxies, for example, gather vast amounts of matter in shared environments. Groups of galaxies also retain broad common reservoirs around their members. Individual galaxies sit inside halos that merge gradually into larger surroundings. Filaments channel matter toward denser nodes and connect one region of structure to another. In this arrangement, boundaries are often not sharp. The edge of a galaxy's visible body is not the edge of its baryonic domain, and the separation between one system and the larger web is often a matter of changing density rather than a hard border. This matters for the missing baryon problem because counting becomes difficult whenever the object of interest has no simple outline. Ordinary matter in the cosmic web belongs to a continuum of structure, with dense nodes at one extreme and rarefied outskirts at the other. By this stage, the search has moved into a new region of the subject. The central question is no longer whether the universe forms the expected amount of ordinary matter, nor whether galaxies alone can hold it. The question becomes how the large-scale web stores that matter across its interconnected terrain. The web is the reservoir because it is where the gravitational map places most of the baryonic material outside the bright interiors of galaxies. It is a universe of connections rather than isolated islands, of long bridges rather than separate points, of diffuse extensions rather than compact containers. The missing baryons belong to that wider setting. They occupy the same large-scale structure that governs the late universe as a whole. Once the cosmic web is understood as the true landscape, the apparent absence of ordinary matter begins to look less like a contradiction and more like a problem of learning to observe the broad, faint, structured medium that binds the visible universe together. The ordinary matter that proves hardest to count is not usually hidden inside dark corners of bright galaxies. It is hidden by its physical condition. Much of it exists as ionized gas, which means the atoms have lost one or more electrons and no longer remain neutral. In this state, the gas is called plasma. Plasma is common in the universe because energetic radiation, shock heating, and large-scale gravitational collapse keep stripping electrons from atoms in low-density environments. Hydrogen, the most abundant element of ordinary matter, becomes especially important here. Neutral hydrogen can leave a strong mark in several kinds of observations, but ionized hydrogen is far less cooperative. Once the electron is removed, the atom no longer produces the same easily traced signature. The matter is still there, still made of ordinary protons and electrons, but its visibility changes sharply. A great part of the missing baryon problem therefore becomes a problem of ionization. Matter disappears from straightforward view, not because it ceases to exist, but because it enters a state in which ordinary detection methods lose their grip. Temperature deepens this difficulty. In the mature cosmic web, a large fraction of the baryons is expected to occupy the warm-hot intergalactic medium. This is gas heated to roughly 100,000 to 10 million Kelvin by the slow growth of cosmic structure, by matter falling into filaments and halos, and by energy released around galaxies and groups. At such temperatures, atoms are partly or strongly ionized. The gas is not condensed into cold clouds, and it is not packed densely enough to shine like the hot plasma in the cores of rich galaxy clusters. It occupies an awkward middle ground. It is too hot for the classic traces of cool galactic gas, yet usually too thin to glow strongly on its own. For many years, simulations indicate that a large share of the uncounted baryons should live in this warm-hot phase, spread through filaments and around galaxies. The theory is persuasive, but the observational challenge remains severe because heat alone does not make diffuse gas easy to see. Density is the other half of the concealment. Bright astronomical emission usually favors crowded environments. When many particles occupy a small volume, collisions and radiative processes become common enough to build a detectable signal. In the intergalactic medium, the gas is spread so thinly that a large cosmic volume may contain only a modest number of particles in any local region. Yet because that thinness extends across enormous distances, the total mass can still be substantial. This contrast between local faintness and total abundance lies near the heart of the missing baryon problem. A filament of plasma may hold an enormous quantity of ordinary matter when considered over millions of light years. While each small patch of that filament remains dim, the eye and the telescope are both drawn toward compact brightness. Diffuse ionized gas offers neither compactness nor much brightness. It is a reservoir by volume rather than by spectacle. The universe stores common matter in a form that is physically ordinary but observationally quiet. Hydrogen makes the situation even subtler because the most abundant baryonic element is also the element whose easiest signature weakens when ionized. In cooler and less ionized conditions, hydrogen can reveal itself through prominent absorption features. In the hotter, thinner regions where many missing baryons are thought to reside, hydrogen is largely stripped of its electron and becomes much harder to trace directly in those same ways. Astronomers can sometimes look for heavier elements such as oxygen in highly ionized states, because those ions still leave measurable marks under favorable conditions. But heavier elements are much less abundant than hydrogen, and their presence depends on how enriched the gas has become through earlier star formation and galactic outflows. This introduces an added uncertainty. A signal from oxygen can indicate warm-hot gas, but it is only an indirect stand-in for the full hydrogen reservoir. The dominant mass remains hydrogen and helium, while the easier clues often come from rarer ingredients. Another difficulty comes from contrast. Diffuse ionized gas must be separated from brighter foregrounds and backgrounds, light from stars, gas inside galaxies, active galactic nuclei, and hot cluster interiors can complicate the picture. Even when intergalactic plasma leaves a trace, that trace may be weak compared with neighboring sources of radiation, or mixed with material belonging to galactic halos. The boundaries are not sharp. A galaxy can grade outward into a halo, and a halo can grade into the larger web. The hidden matter is not arranged as a set of isolated clouds with clear edges. It belongs to a continuum of ionized material whose density, temperature, and composition change gradually across large regions. Observation must work against that smoothness. For these reasons, the missing baryons remain difficult to recover through direct imaging alone. A camera is best at seeing what emits or reflects strongly. The ionized gas between galaxies often does neither at a level that is easy to map broadly. Even when it emits, the signal can be weak and confined to bands that require special instruments and long observing times. Absorption studies provide another route, but those too rely on fortunate alignments and extremely sensitive measurements. Ordinary matter in this phase is not hidden by rarity. It is hidden by diffuseness, ionization, and scale. The cosmic web is therefore not empty in the usual sense. It is filled with a thin plasma fog whose mass becomes impressive only when the full depth of intergalactic space is taken into account. So this region of the story settles into a quiet conclusion. The missing ordinary matter is difficult to see because much of it is hot enough to be ionized, thin enough to be faint, and spread widely enough that its mass hides inside volume rather than brightness. It is not locked safely inside the stars that dominate night skies, and it is not arranged as neat visible clouds. It drifts through the large-scale structure as a tenuous plasma, occupying the long filaments and extended surroundings of galaxies. The problem of the missing baryons is therefore not only a matter of where the material lies, it is equally a matter of what state that material occupies. Once ordinary matter becomes ionized and diffuse, the familiar signatures of atoms grow weak, and the universe keeps much of its common substance in a form that is present across the web, yet almost nowhere obvious to sight. Once ordinary matter is understood as a diffuse component of the cosmic web, the search changes from looking at objects to studying paths. Astronomers begin to think in terms of a line of sight, which is the straight observational path from Earth to some distant source of light. That path may look empty in an image, yet physically it is not empty at all. It passes through the Milky Way, through any gas around the Milky Way, through intergalactic space, through halos surrounding other galaxies, and through the filaments and thinner regions of the larger cosmic web. A single line of sight therefore becomes a narrow sample through many layers of cosmic material. The universe is not only a set of separate things to be photographed, it is also a medium that can be crossed, and anything that crosses it can carry the imprint of what lies along the way. This idea is gentle but powerful. Matter that is too faint to see directly can still reveal itself if it interacts with radiation from something more distant. The background source does not need to belong to the same system as the intervening gas. It only needs to shine from farther away, so that its light travels through the material before reaching the observer. In this way, the line of sight acts almost like a probe lowered through layers that would otherwise remain invisible. The observer does not need the gas itself to glow strongly. The gas only needs to alter the passing signal in a measurable way. For decades, one of the most sensitive ways to study very diffuse gas has been absorption line spectroscopy, which uses bright background sources such as quasars or galaxies to test what lies along the path between source and observer. The method is especially valuable for low-density circumgalactic and intergalactic gas, because such gas often leaves clearer traces in passing light than it does in its own emission. The key quantity along such a path is not always local density at one point. It is often column density, which means the total amount of material integrated along the line of sight. A very thin region can contribute meaningfully if the path through it is long enough. This is one reason intergalactic matter, though tenuous, can still produce measurable effects. A single small parcel of the gas may be almost negligible. A path that crosses millions or billions of light-years of similar material can add those tiny contributions together. The result is a cumulative trace that reflects the total amount of intervening matter, rather than the dramatic appearance of any one place. This way of measuring suits the cosmic web well, because the web hides much of its baryonic mass in long, extended structures rather than compact bright bodies. What is difficult to image directly may still become legible when measured as an accumulated effect along depth. A line of sight also carries a certain humility. It does not present a full three-dimensional map all at once. It provides one narrow thread of evidence through a much larger volume. Along that thread, different environments can overlap in effect. Gas in a galaxy halo may contribute. Gas in a filament may contribute. Sparse material in a broader intergalactic region may contribute. Each segment adds its small part, and the observer sees the sum. This is both a strength and a limitation. The strength is sensitivity, because even very faint material can matter when many contributions are added together. The limitation is that the total signal must later be interpreted, separated, and compared with other information in order to determine where the material actually lies. A sight line does not immediately display cosmic geography. It records the integrated influence of geography along one path. This integrated view has shaped the study of diffuse gas for many years. Quasar spectra, for example, reveal the intergalactic medium as a dense pattern of absorption features, often called the Lyman alpha forest. That pattern shows that the space between galaxies is filled with gaseous structure rather than simple emptiness. It demonstrates that a distant background source can be used to probe matter, distributed across large portions of the universe. In this approach, the distant source matters less as an object in its own right, and more as a steady lamp behind the material of interest. The path becomes the subject. The source merely provides the illumination. This is a quiet reversal of ordinary astronomy. Instead of studying the bright thing directly, astronomers study the dim medium that lies in front of it. Because the cosmic web is structured, no two sight lines are exactly alike. One path may pass through a richer filament, another through a thinner region, another close to a galaxy halo, another through more nearly empty territory. This variation is not a nuisance alone. It is also valuable information. By comparing many lines of sight, astronomers can begin to infer how baryonic matter is distributed across different environments. One path provides a sample. Many paths begin to outline a statistical map. This is especially important for matter that is too diffuse to draw in ordinary images. The web may resist direct portraiture, yet it can still be studied through repeated narrow traverses across many directions. The universe then yields its hidden matter, not in one grand picture, but in an accumulation of slender measurements. So the line of sight becomes a disciplined way of thinking about intergalactic space. It treats the region between galaxies as a real physical medium with depth, structure, and measurable influence. It accepts that ordinary matter may be too diffuse to stand out as a bright object, while still insisting that the matter can leave a trace on radiation that crosses it. In this region of the subject, the search for missing baryons becomes less a hunt for hidden bodies and more a study of cumulative passage. A distant signal travels. The cosmic web lies in the way. The path gathers the imprint of that encounter. In a universe where much ordinary matter lives outside bright galaxies, the most revealing evidence often comes not from what shines by itself, but from what quietly alters the light that passes through. Into this vast, faint setting, there appears a different kind of object, not a galaxy to be photographed at leisure, and not a steady beacon that shines for ages, but a flash, a fast radio burst, usually shortened to FRB, is a brief pulse of radio emission, arriving from beyond the Milky Way. Its defining feature is suddenness. The signal rises and is gone within only a few milliseconds, leaving behind a record that is short in time but rich in information. In ordinary human experience, such brevity suggests fragility. In astronomy, the brevity of an FRB does not make it weak. These bursts are intensely bright at radio wavelengths while they last, bright enough to be detected across enormous cosmic distances. Their sources remain among the most intriguing unresolved subjects in high-energy astrophysics. But their observational identity is clear. They are remote, transient, radio flashes that cross the universe and briefly announce themselves before silence returns. The first recognized FRB enters astronomy through archival data rather than a planned sighting. In 2007, researchers report a striking dispersed radio pulse in earlier observations, an event that later becomes widely known as the Lorimer burst. Over time, more examples appear, and what first seems like a singular oddity becomes a class of sources. As the sample grows, the case strengthens that these bursts are real astrophysical events rather than instrumental mistakes. Their durations remain extremely short, their arrival times unpredictable, and their signals shaped in ways consistent with passage through ionized material. With improved surveys and wider radio monitoring, FRBs move from curiosity to established phenomenon. Today they are detected in substantial numbers by facilities such as ESA and CHIME, and they form one of the most rapidly developing subjects in observational astronomy. Their short duration carries an immediate physical meaning. A source cannot vary much faster than light can cross the region producing the signal, so an event that lasts only milliseconds must come from a very compact site. This does not yet reveal the exact engine, but it narrows the scale sharply. The source must belong to a relatively small region, associated with an energetic astrophysical object. Many ideas have been proposed, and current evidence strongly supports at least some FRBs arising from magnetars, which are highly magnetized neutron stars. Even so, the full FRB population may not be explained by one simple channel alone, and it remains uncertain whether every burst comes from the same kind of source environment. What matters at this stage is the observational character. FRBs are not broad radio glows spread across galaxies. They are compact outbursts from distant astrophysical systems, carrying a great deal of energy through a remarkably brief signal. Their distances are essential. Several FRBs have now been localized to host galaxies well beyond the Milky Way, confirming that they are extragalactic and often cosmological in reach. This means the bursts do not merely cross a local neighbourhood of gas, they traverse enormous stretches of space before arriving at Earth. One striking example is FRB2 0220610A, whose light travels for about 8 billion years before detection, making it the most distant, well-localized FRB reported to date. A burst like this is not only a dramatic event at its source, it is also a signal that has sampled a long fraction of the visible universe during its journey. The farther the burst, the more intergalactic territory lies between source and observer, and the more valuable the burst becomes as a tracer of the medium it crosses. Even before one considers the exact measurement technique, the importance of distance is already plain. These are not local sparks. They are far-travelling radio flashes seen across the deep structure of the cosmos. Brightness gives them their utility. An FRB lasts only a tiny interval. Yet during that interval it can outshine, in radio terms, far more persistent sources at similar distances. The signal therefore stands out against background noise and can be timed with great precision. Because the burst is so short, small changes impressed upon it during travel are easier to measure than they would be in a long, slowly varying source. A steady radio emitter can also probe intervening matter, but a sudden pulse has a special advantage. Its structure in time provides a clean clock. The burst leaves the distant galaxy in one compact episode, and the received signal preserves the imprint of the medium encountered along the way. In this sense, an FRB behaves like a cosmic flashlight switched on for an instant in a faraway system. The light is brief, but the path it illuminates is immense. There is also a useful observational simplicity to FRBs. They are defined first by what is seen, not by a complete theory of what makes them. Astronomy often advances in this order. A phenomenon becomes real through repeated detection, stable patterns, and measurable properties before its deeper cause is settled. FRBs fit this pattern well. Observers know they are short radio transients. They know many are extragalactic. They know some repeat while others are seen only once so far. They know the signals carry the mark of passage through plasma. They do not yet know whether one source class explains the whole population. This mixture of clarity and uncertainty makes FRBs especially valuable. The phenomenon is robust enough to use, even while its origins remain under active study. At this outer observational layer, the burst is best understood as a distant radio lamp that flashes from far beyond the Milky Way. It appears against the larger setting already described a universe whose ordinary matter is spread thinly through halos and intergalactic space, because the burst crosses that setting rather than merely shining within one nearby region. It can carry evidence of the material encountered on the journey. The source itself may be compact and violent, but what makes the burst so useful is not only what happens at its origin, it is the fact that the signal remains coherent enough to arrive after crossing billions of light-years of structured space. A fast radio burst is therefore both an astrophysical event and a travelling probe. Seen from this wide perspective, it is a brief messenger from deep time and deep distance, bright enough to be noticed and short enough to preserve the record of cosmic passage. Seen only as a signal, a fast radio burst is a small event on a time axis and a surprisingly rich event everywhere else. It lasts for only a few milliseconds in the form first recognized by most surveys. Yet that short interval often contains internal structure, changing brightness, selective frequency coverage, and distinct polarization. The burst is not a simple dot in a radio receiver. It is a compact packet of information. In a telescope record, it can appear as a sharp rise of power, sometimes with one main peak, sometimes with several components clustered close together, and sometimes with finer detail emerging when the data are recorded at higher time resolution. What seems at first like a single flash often proves to have internal texture. This is one reason FRBs move so quickly from curiosity to serious observational subject. Their duration is brief, but their signals are not plain. The basic timescale remains the first striking feature. Most FRBs are discovered with durations of a few milliseconds or less, placing them among the shortest known extragalactic radio transients. Even this familiar statement turns out to be only a surface description. With better instruments and baseband recording, some bursts reveal much narrower internal components. A repeating source in the nearby galaxy M81 has shown structure below 100 nanoseconds, which means the burst is not merely short by ordinary astronomical standards, but capable of changing on astonishingly fine time intervals. Other sources have shown sub-microsecond detail and compact components nested inside a broader burst envelope. This range of timescales suggests that the observed burst is often a layered signal, a millisecond event on the outside, with much smaller time structure inside. The burst therefore resembles a compressed landscape rather than a single smooth pulse. Its frequency behavior is equally selective. An FRB is a radio burst, but it does not always illuminate an entire observed radio band evenly. Many bursts appear stronger in only part of the band, and some repeating bursts are notably narrow-band, occupying a limited frequency range at a given moment. In a dynamic spectrum, which is a record of brightness as a function of both time and frequency, the signal can look patchy rather than continuous. Some portions of the band brighten while others remain faint. Some bursts show several islands of emission separated across frequency. This means an FRB is not just a clock event, it is also a spectral event, with its own momentary shape in radio frequency space. Such behavior has become one of the defining observational features of repeating sources in particular, though the wider population shows great variety. The burst does not fill the available receiver band as a uniform flash. It chooses parts of the band, often in ways that change from one event to the next. Many FRBs also show subbursts, which are smaller emission components embedded inside a larger event. A burst may begin with one bright feature and then display one or more additional components close behind it. These are not separate astrophysical sources. They are pieces of one detected burst. In repeating FRBs, the internal arrangement of these components can become especially intricate. Observers see fine structure that shifts, clusters, and varies in strength from burst to burst. Some sources even show quasi-periodic or highly regular substructure on very short timescales, suggesting that the observed signal is shaped by a precise and possibly changing engine or propagation environment. Whatever the deeper cause, the phenomenological point is clear. FRBs are not always single, clean spikes. They can be internally segmented events with multiple features crowded into a tiny fraction of a second. Another major property is repetition. Some FRB sources are seen only once so far, while others produce repeated bursts over days, months, or years. This does not necessarily divide the population into two completely separate physical classes, but observationally the contrast is real. Repeating sources allow astronomers to gather many examples from the same sky position and compare how the signal changes from one outburst to the next. These repeaters often display especially rich time-frequency structure and wide variations in activity level. At times they become hyperactive, producing many bursts in a short observing campaign, then growing quiet again. Apparent non-repeaters may be intrinsically different, or they may simply burst less often or below current sensitivity thresholds. For the observational description of the signal itself, the important point is that an FRB source can behave either as a solitary event in the data or as a recurring radio transient with an evolving signal character. Polarization adds another layer of structure. Polarization describes the orientation and form of the electromagnetic wave, and in FRBs it is often strong. Many bursts show high linear polarization, which means the electric field of the radio wave is organized rather than random. Some bursts also show circular polarization, where the field rotates as the wave travels. In a few cases, the circular fraction becomes remarkably high. The polarization can change across a single burst, and the position angle of the linearly polarized part can evolve through the event. These details matter because they show that the burst is not simply bright noise. It is a highly ordered radio signal. Even before the physical origin is fully agreed upon, the observed polarization alone tells astronomers that the emission and its surrounding environment are structured and extreme. The signal arrives not only with brightness, but with geometry encoded into the wave itself. The bursts also carry the marks of broadening and distortion. Some arrive as crisp, narrow events, others are smeared slightly in time, with a trailing tail that makes the burst appear less sharp. This is often described as scattering, an effect that roughens the radio path and spreads the signal out over a short interval. The degree of scattering differs strongly from burst to burst and from source to source. At lower radio frequencies, some repeaters show especially pronounced propagation-related structure, while others remain comparatively sharp. There can also be scintillation, a kind of twinkling caused by small-scale irregularities along the path. These effects are part of the observed character of FRBs, even before one assigns each contribution to a specific region of space. The burst that leaves a distant source as a compact radio event does not always reach the telescope in a pristine form. The received signal may already carry the fingerprint of an uneven journey. Taken together, these properties make an FRB a distinctive kind of astronomical signal. It is extremely brief, often intensely bright, sometimes internally fragmented, often frequency selective, frequently polarized, and occasionally repeated from the same source. It can contain fine temporal detail far below the millisecond scale first used to define the class. It can vary dramatically from one burst to the next even when the source position stays fixed. This variability is not noise hiding a simple event, it is part of the event itself. The observed burst is a layered radio phenomenon whose outward brevity conceals a complicated structure in time, frequency, and wave orientation. Seen in this way, an FRB is not merely a flash. It is a compact radio record with enough structure to support both astrophysical interpretation and precision measurement. A fast radio burst leaves its source as one brief event, but it does not arrive at Earth in that same simple form. Along the long journey, the signal crosses plasma, which is ionized gas containing free electrons. These electrons matter because radio waves do not move through plasma in exactly the same way that they move through empty space. The vacuum speed of light remains one of physics' deepest constants, but in a medium the signal's passage can be altered. In the case of an FRB, the most important change is a delay that depends on frequency. Higher radio frequencies pass through more quickly. Lower radio frequencies are held back slightly. The burst therefore reaches the telescope not as one perfectly simultaneous flash, but as a swept signal in which the upper part of the radio band appears first and the lower part follows after it. This is one of the defining observational marks of an FRB. and it is the reason these bursts become so useful for studying the diffuse plasma between galaxies. The effect is called dispersion. Dispersion means that different frequencies of the same wave packet travel through a medium at different effective speeds. In plasma, this happens because the radio wave interacts with the free electrons in the gas. As the electromagnetic field of the wave passes through, the electrons respond to it. Their motion does not absorb the whole signal, but it does alter the way the wave propagates. The result is not a random scrambling. It is a very orderly effect. The lower the radio frequency, the more strongly the signal is delayed. The higher the frequency, the less delay it experiences. This gives the arriving burst a characteristic shape across time and frequency, a downward sweep in which the top of the observing band appears first and the bottom arrives later. Even when the burst itself lasts only milliseconds at the source, the spread in arrival time across the band can be much larger because the journey through plasma stretches the signal. This stretching is gentle in any one small region of space, but the path of an FRB is immense. The burst crosses the plasma of its local environment, the gas of its host galaxy, the extended material around that galaxy, the intergalactic medium, any intervening halos or filaments, and finally the gas associated with the Milky Way before reaching the telescope. Each region contributes a small part of the total delay. No single electron does anything dramatic. No small parcel of gas transforms the signal by itself. The power of the effect comes from accumulation. The wave travels through a vast column of ionized material, and the tiny influence of countless free electrons adds up. By the time the signal reaches Earth, the total delay can be unmistakable. A burst that begins as one compact event is spread across observing frequencies into a clear time sequence, with high radio tones arriving before low ones. This is why dispersion is so striking in fast radio bursts. The bursts are short, bright, and sharply timed, so the medium has something precise to act upon. If the source emitted a broad, slowly varying signal, the effect of plasma delay would be harder to read cleanly. But an FRB is more like a sudden mark on a timeline. The intervening plasma takes that mark and pulls it into an ordered sweep. In telescope data, this sweep can be seen directly before any deeper interpretation begins. The signal bends across the plane of time and frequency in a way that shows at once that it has not crossed empty space alone. The burst has travelled through ionized matter, and the matter has left its signature on the arrival pattern. The physics of the effect remains calm and consistent. Free electrons are light and mobile, so they respond readily to passing radio fields. Their collective response changes the propagation of the wave through the medium. The influence is strongest at lower frequencies because those waves interact more strongly with the plasma on the relevant timescale. Higher frequencies are less affected and therefore stay closer to the timing they would have in empty space. The difference is not a change in the source event itself. It is a change imposed during travel. The source emits one burst. The medium turns that burst into a frequency-ordered arrival. In this sense, plasma acts less like a wall and more like a slow filter. It does not stop the burst. It delays parts of it by predictable amounts. The radio signal survives the crossing, but it emerges with a memory of the material it has passed through. This memory is especially valuable because the plasma involved is often too diffuse to see directly. The signal becomes readable precisely because the matter does not need to shine on its own. It only needs to be present along the path. The FRB therefore brings news of otherwise quiet regions. It does not photograph them. It records their influence. The effect also helps distinguish fast radio bursts from many kinds of local interference. Human-made radio noise can mimic sudden signals, but it often lacks the clean, cold plasma sweep expected from a true astronomical burst. A genuine dispersed burst shows a specific pattern, high frequencies first, low frequencies later, in a smooth and ordered progression across the band. This pattern is not arbitrary. It reflects the well-understood behavior of radio waves in ionized gas. For astronomers searching huge data streams for rare events, that pattern becomes one of the clearest signs that the signal has crossed cosmic plasma rather than being produced nearby on Earth. Dispersion does not act alone. A burst can also be scattered, twinkled, or otherwise distorted by uneven material along the path. But dispersion is the most fundamental large-scale timing effect. It is the broad sweep laid over the entire signal, the mark of plasma acting through depth rather than through local turbulence. Scattering can blur the burst. Dispersion rearranges its arrival by frequency. One effect softens the shape. The other creates the ordered delay that makes the burst look as though it is sliding downward through the band. At this stage of the story, nothing more is required than the basic fact of the delay itself. A fast radio burst crosses the ionized material of the universe. Free electrons along the way slow the lower radio frequencies more than the higher ones. The burst therefore reaches Earth in layers of frequency rather than all at once. This is the visible sign of invisible plasma. It is the quiet action of diffuse ordinary matter on a travelling signal. Across billions of light years, a very thin medium leaves a clear mark, and a momentary flash becomes a record of passage through the ionized web of the cosmos. The delay across radio frequencies becomes scientifically powerful only when it is treated as more than a visual pattern. Astronomers give that pattern a quantity called dispersion measure. This is the total column of free electrons along the line of sight, added up from the source to the observer. In simple terms, it is not a count of how many electrons sit in one small place. It is a count of how much electron-filled plasma the signal crosses in total. The burst arrives at high frequencies first and low frequencies later, and the size of that delay follows a well-understood law for cold plasma. Because of that law, the observed sweep can be translated into a single number. That number summarizes the integrated electron content of the whole journey. The burst stops being only a strange signal shape in a telescope record. It becomes a measurement of the otherwise invisible ionized matter distributed along the path. This translation depends on regularity. Dispersion in plasma does not distort the signal in an arbitrary way. The delay grows larger toward lower radio frequencies in a precise and predictable fashion. When astronomers search burst data, they test many possible values of dispersion measure and ask which one best realigns the signal across the observing band. If the correct value is used, the burst sharpens. Emission that appears spread across time at different frequencies collapses back toward a single compact event. If the wrong value is used, the burst remains smeared. This practical step is one of the most important parts of FRB discovery and analysis. It turns a slanted sweep into a recoverable intrinsic burst and, at the same time, yields the number that records the total electron column crossed during travel. In this sense, dispersion measure is not an abstract theoretical quantity placed on the data afterward. It is extracted directly from the way the burst sharpens when the plasma delay is properly removed. The meaning of the quantity is cumulative. A larger dispersion measure does not necessarily imply denser plasma at every point. It means that the total contribution from free electrons along the full path is larger. A very long path through modest plasma can produce a substantial value. A shorter path through denser material can also do so. What the burst records is the sum. This is why the measure is so valuable for the missing baryon problem. The hidden ordinary matter in the cosmic web is often too diffuse to shine clearly, but it still contains free electrons. Those electrons do not need to announce themselves by bright emission. It is enough that they sit in the way. Their integrated presence slows the burst in a measurable manner, and the delay reveals the total electron column even when the plasma itself remains visually faint. Dispersion measure therefore matches the observational challenge of the intergalactic medium very well. It is sensitive to depth rather than brightness. This makes FRBs especially different from many older tools of gas detection. Traditional emission studies are strongest where gas is concentrated enough to glow. Absorption studies are strongest when certain atoms or ions leave recognizable lines against a background source. Dispersion measure offers another route. It is not primarily a line feature from one element, and it does not require a dense glowing region. It responds to the total population of free electrons, wherever they are distributed along the path. Since ionized hydrogen provides one free electron per atom, and helium adds further electrons according to its ionization state, the measure acts as a broad tracer of ionized baryonic matter. It does not identify every atom species one by one. Instead, it registers the collective electron content of the plasma. That makes it unusually well suited to diffuse intergalactic matter, where the gas is widespread, highly ionized, and difficult to map by ordinary brightness alone. There is also a natural proportionality in the method. Other things being equal, a burst that travels through more ionized material accumulates a larger delay between high and low frequencies. A burst that crosses less ionized material accumulates a smaller one. This does not mean the interpretation is trivial, because many regions can contribute to the total, but it does mean the signal carries a physically meaningful integral of the intervening plasma. The burst acts almost like a running tally taken over distance. As each segment of plasma is crossed, the total increases by a tiny amount. No observer watches that increase happen continuously through space. What arrives at the telescope is the finished sum, written into the timing difference across the radio band. From that sum, astronomers infer how much free electron material the burst has traversed, in a universe where ordinary matter is hidden by diffuseness. Such an integrated tally is exactly the kind of information that direct imaging struggles to provide. The term dispersion measure can sound more technical than it is. In practice, it simply names the amount of plasma influence required to produce the observed sweep. A burst with a very small value would look only lightly delayed across the band and would suggest a shorter or cleaner plasma path. A burst with a very large value would require a much greater total column of free electrons. Many FRBs are striking because their values are far larger than what the Milky Way alone can easily explain, which is one of the clues that supports their extragalactic nature. The burst appears to have crossed much more ionized material than a local galactic source usually would. This is one of the reasons dispersion measure becomes central from the earliest days of FRB research. It is both a discovery tool and a physical indicator that the signal belongs to the wider cosmos. Yet the elegance of the measure lies in its restraint. Dispersion measure does not by itself provide a full map of where each electron sits. It gives the total column, not the detailed geography. Still, that total is extraordinarily valuable because it transforms a fleeting radio flash into a quantitative probe of invisible matter. Before the burst is analyzed, one sees only a dispersed signal. After the delay is measured and understood, one has a line-of-sight electron census. The signal has become an instrument. The arrival times of different radio frequencies, carefully compared, turn into a weighing method for plasma spread through galaxies, halos, and intergalactic space. In that conversion, the hidden ordinary matter of the universe begins to leave the realm of inference alone and enters the realm of countable observation. The dispersion measure of a fast radio burst is never born as a purely intergalactic quantity. What the telescope records is a total. That total includes every significant population of free electrons between the source and Earth. Before astronomers can use the burst to study matter across the broader universe, they must first account for the nearby plasma that belongs to the Milky Way and its immediate surroundings. In practical work, the observed dispersion measure is usually treated as a sum of several terms: the Milky Way interstellar medium, the Milky Way halo, the intergalactic medium, and the contribution from the host side reduced by cosmic expansion. This decomposition is conceptually simple, but the nearby foregrounds matter greatly because they are the first layers crossed on the final approach to Earth. If those local layers are not estimated and removed, the wider cosmic interpretation remains blurred. The first nearby contribution comes from the Milky Way interstellar medium, which is the ionized gas distributed through the galactic disk, spiral arms, and local structures. A burst seen close to the galactic plane generally crosses more of this material than a burst seen at high galactic latitude, where the line of sight leaves the dense disk more quickly. This means the Milky Way foreground is not one universal number. It depends strongly on direction. Some sightlines pass through rich regions of free electrons associated with the inner disk, spiral arm crossings, or nearby ionized complexes. Other sightlines climb more directly away from the disk and encounter a smaller galactic column. The sky, therefore, comes with a built-in pattern of local electron thickness, and every FRB must be judged against the particular foreground of its own coordinates. To estimate this foreground, astronomers use galactic electron density models built largely from pulsar data. Two of the most widely used are NE 2001 and YMW 16. Both attempt to describe the three-dimensional distribution of free electrons in the Milky Way, but they do not agree perfectly, because the galaxy is structurally complex and the available calibrating sources do not sample every direction equally well. These models include large-scale disk components and spiral structure, along with localized features where possible, and they are used to integrate the expected galactic contribution along a chosen line of sight. When an FRB is detected, one of the first practical steps is therefore to ask what NE 2001 or YMW 16 predicts for that position on the sky. The answer provides a baseline estimate of how much of the observed dispersion measure may belong to the Milky Way itself. Yet this foreground estimate is never perfectly exact. The Milky Way is not a smooth laboratory medium. It contains irregular structure, local bubbles, spiral arm complexity, and sightline to sightline variation that no model can capture completely. Recent studies note that NE 2001 and YMW 16 can diverge significantly in some directions and show limitations, especially where independent calibrators are sparse, or where high-latitude behavior is less securely constrained. This does not make the models useless. It means their results must be treated as informed estimates rather than flawless subtractions. For a very large extragalactic dispersion measure, the galactic disk term may be a relatively modest correction, for smaller totals, or for precision cosmological work. The uncertainty in that correction becomes more important. The local foreground is not merely something to subtract once and forget. It is one of the main systematic terms that must be carried carefully through the analysis. Beyond the galactic disk lies the Milky Way halo, a much broader and more diffuse envelope of hot ionized gas surrounding the galaxy. This halo is especially important because it extends far beyond the bright stellar body and contributes free electrons even when a burst is seen at high galactic latitude. In other words, leaving the dense plane of the Milky Way does not mean leaving the Milky Way's baryonic influence entirely. The halo remains. It is thinner than the disk but far more extended, and because the path through it can still be long, it contributes a non-negligible share to the total dispersion measure. In many FRB analyses, this halo term is treated as being on the order of tens of parsecs per cubic centimetre, with 40 parsecs per cubic centimetre often used as a representative working value, though the true value likely varies with direction and halo structure. The halo term is also one of the more stubborn nearby uncertainties. Unlike the galactic disk, it is not mapped through a dense network of pulsars distributed across the whole halo volume. Its density profile, temperature structure, and outer extent remain subjects of active study. Models constrained by X-ray observations and theoretical considerations tend to favour lower values within a plausible range. But the full contribution is still not pinned down with perfect confidence. This matters because the halo belongs to the foreground that must be removed before the remaining signal can be interpreted as intergalactic. If the halo contribution is overestimated, the cosmic share is pushed too low. If it is underestimated, the cosmic share is pushed too high. The halo therefore sits at an important boundary between the local galaxy and the broader baryonic census. It is nearby enough to subtract, yet diffuse enough to remain partly uncertain. Once the disk and halo are both considered, the foreground subtraction becomes a matter of careful accounting rather than dramatic discovery. Astronomers begin with the observed dispersion measure, estimate the Milky Way disk contribution from a galactic electron model, add an allowance for the Milky Way halo, and then examine what remains. That remainder is the extragalactic share, though even that extragalactic share is not purely intergalactic because the burst's host system also contributes. At this stage, however, the crucial task is only to clear the nearby screen. The goal is to remove as much of the local electron column as current knowledge allows, so that the remaining signal no longer belongs mainly to the Milky Way. Only then can the burst begin to speak clearly about matter beyond the galaxy. This foreground cleaning also helps explain why FRBs are recognized as extragalactic in the first place. Many bursts show dispersion measures far above what the Milky Way disk alone can account for, and even after reasonable allowance is made for the halo, a substantial excess remains. That excess is one of the strongest early clues that the signal has crossed a great reach of ionized material beyond the galaxy. The local foreground does not erase the cosmological value of FRBs, it sharpens it. By identifying and removing the nearby plasma terms, astronomers convert a raw total into a more meaningful remainder. The Milky Way stops being an unmeasured contaminant and becomes a known, though imperfectly known, first layer in the path. So this region of the story remains close to home. Before the missing baryons of the wider universe can be counted, the burst must first be cleaned of the electrons nearest to Earth. The Milky Way disk contributes by direction, structured by spiral arms and local ionized regions. The Milky Way halo contributes by extension, surrounding the galaxy in a broad plasma envelope. Together they form the nearby foreground that every FRB must cross and every analyst must estimate. The act of subtraction is quiet but essential. It removes the familiar galaxy from the total so that the deeper path beyond it can be read with greater clarity. In a subject built on cumulative passage, even the first local layers must be measured with care before the wider universe can be weighed. A fast radio burst can reveal that a great column of ionized matter lies along its path, but that information remains incomplete until the burst is tied to a specific place in the sky with enough precision to identify the galaxy from which it comes. Discovery alone is not enough. Many radio telescopes first detect FRBs with beams that cover large areas of sky, and within such an area there may be many galaxies. A burst that is only roughly placed has no secure home. Without a secure home, the signal remains detached from a measurable cosmic setting. It is known to be extragalactic in a broad sense, because its dispersion measure is too large for the Milky Way alone, but its exact origin remains uncertain. The burst is then like a message with no return address. For the study of missing matter, that uncertainty matters deeply, because the burst can only become part of a precise baryon census once astronomers know which galaxy launched it. This need gives rise to localization, the process of determining an FRB position with far greater accuracy than the initial detection often provides. In radio astronomy, better angular precision usually comes from interferometry, which combines signals from multiple antennas spread across a landscape. When many dishes or stations observe together, the effective instrument becomes much larger than any single dish. The sky position of a burst can then be constrained much more tightly, in some cases to a fraction of an arcsecond. At that level of precision, the radio position can be overlaid on deep optical and infrared images, and a likely host galaxy can be identified. Localization is therefore not merely a technical refinement. It is the act that converts a burst from a floating transient into an event anchored in the visible universe. The task is difficult because FRBs are brief and unpredictable. A transient that lasts only milliseconds is not easily revisited after it has passed. If the array does not capture the burst with sufficient timing and positional information at the moment of detection, the opportunity may be lost. This is why instrument design becomes so important in FRB astronomy. Some facilities prioritize a wide field of view and detect many bursts, but with coarser positions, others are built or operated in ways that allow rapid interferometric localization, real-time alert systems, voltage capture, baseband recording, and prompt follow-up all become part of the effort. The challenge is to preserve enough information from that tiny interval of arrival so that the sky location can later be reconstructed with confidence. A burst that lasts only a few milliseconds can require an entire chain of preparation, recording, and analysis to be pinned to one galaxy. Repeaters offer one route through this difficulty. If a source bursts more than once, astronomers can return to the same patch of sky and wait for additional events. Each new burst gives another chance to improve the position and gather more information. This is why repeating sources play such an important role in the early history of FRB localization. When repeated bursts are seen from the same origin, the source ceases to be a one-time flash and becomes a persistent target of observation. Radio arrays can then localize it more accurately, and other telescopes can inspect the candidate host galaxy in detail. The first well-localized repeating FRB demonstrates the power of this method by linking the burst source to a dwarf galaxy at cosmological distance. That result changes the field. It proves that at least some FRBs are not local galactic oddities and not instrumental artifacts. They belong to real host galaxies in the wider universe. Non-repeating bursts can also be localized, but the task is less forgiving because the key event may happen only once within the available observations. In such cases, localization depends on the detection system being ready at the exact moment of arrival. Wide-field interferometric arrays become especially valuable here because they can both discover and place a burst at nearly the same time. This capability grows steadily with newer instruments. Once the burst position is tight enough, Astronomers search for a host galaxy coincident with that location. If only one plausible galaxy lies within the error region, the association can be strong. If more than one lies nearby, statistical reasoning, follow-up data, and properties of the candidate galaxies must be weighed carefully. The aim is not to find any nearby galaxy, but to find the one that the burst truly belongs to. A host galaxy provides several kinds of context at once. It gives the burst an environment, a stellar population, a place within cosmic structure, and a measurable redshift if the galaxy spectrum can be obtained. Even before redshift is used quantitatively, the host itself matters because it establishes the burst as part of a known extragalactic system. The event is no longer just a radio flash with a large dispersion measure. It becomes a burst from a dwarf galaxy, or from a spiral arm, or from the outskirts of a more massive system, or from a star-forming region, or from an older stellar population. These differences carry clues about source physics, but they also matter for the plasma budget. A burst born deep inside a dense galactic environment may encounter more local ionized material than one produced in a cleaner region. The host is therefore not only an address, it is part of the path. The quality of the host association depends on precision and patience. Optical images may reveal faint galaxies that are not obvious at first glance. Spectra must often be taken to determine redshift and physical character. In some cases, a persistent radio source or another multi-wavelength feature is found near the FRB position, adding further context. In other cases, the host remains relatively ordinary and quiet. What matters most is not how dramatic the galaxy appears, but how securely it can be connected to the burst. A false host would distort the scientific interpretation. It would assign the wrong environment, the wrong distance, and the wrong contribution from local plasma. Localization must therefore be accurate enough, and the host identification careful enough that the association is scientifically defensible. As more bursts are localized, the FRB population begins to look less uniform. Hosts span a range of galaxy types and stellar environments. Some bursts arise from vigorous star-forming regions, which supports the idea that at least part of the population is linked to young, highly magnetized neutron stars. Others appear in more mature galactic settings, suggesting that the class may not come from one path alone. This diversity is important for source studies, but in the present context it serves a simpler purpose. It shows that each localized FRB must be treated as a specific event in a specific galactic environment. The burst is not only a signal crossing the universe, it is a signal launched from one particular address within it. By the time localization succeeds, the FRB has undergone a quiet transformation. At discovery, it is a transient radio sweep with a large dispersion measure and no secure home. After localization, it becomes a burst attached to one galaxy among billions. Its position on the sky is precise. Its origin is no longer generic. The vast path between source and Earth remains invisible, but both ends of that path are now better defined. Earth lies at one end, inside the Milky Way foreground already accounted for. A host galaxy lies at the other. Between those two anchored points, the burst has travelled through the plasma of the cosmos. Localization does not yet weigh that journey by distance. It does something more basic and essential. It gives the burst an address, and in doing so it turns a fleeting radio event into a traceable event in the mapped universe. Once a fast radio burst is localized to a host galaxy, the signal gains something it does not possess before a measurable place in cosmic expansion. That place is usually expressed through redshift, which is the stretching of light to longer wavelengths as the universe expands. A host galaxy spectrum can reveal this redshift with high precision, and from it astronomers infer how far back in cosmic time the burst is seen and how much expanding space lies between source and Earth. The burst then has two crucial quantities at once. It has a dispersion measure, which records the integrated free electron column along the path, and it has a host galaxy redshift, which provides the path's cosmological scale. This pairing is the turning point that changes an FRB from an isolated transient into a calibrated probe of the matter between galaxies. Before localization, dispersion measure alone cannot securely separate a nearby dense path from a more distant diffuse one. A large electron column might arise from a very long journey across the cosmic web, or from a shorter journey combined with substantial local plasma near the source, or from some mixture of both. Redshift supplies the missing coordinate. It does not map every parcel of gas, but it anchors the burst in the expanding universe and allows the observed electron total to be compared against a known cosmic scale. Once many localized bursts are assembled, astronomers can compare dispersion measure and redshift statistically and ask whether more distant bursts, on average, show larger extragalactic electron columns. The answer is yes. That rising trend is now one of the central empirical foundations of FRB cosmology. This connection is often called the Macquarie relation, after the study that demonstrated with localized FRBs that the extragalactic dispersion measure rises with redshift in the way expected if ordinary ionized matter fills intergalactic space. The relation is not a razor-thin line. It has scatter, because every sightline crosses a different arrangement of halos, filaments, and host environments. Still, the average trend is what matters first. More distant bursts tend to accumulate more delay from more intervening free electrons. That simple statement turns the diffuse plasma of the cosmic web from a theoretical reservoir into an observable one. It shows that the universe's hidden ordinary matter is not merely guessed from simulations. It leaves a measurable statistical signature in the arrival times of localized radio bursts with known host galaxy redshifts. The importance of redshift here is quiet but deep. Redshift is not merely a substitute for distance in everyday terms. It also tells astronomers where the burst sits within the history of cosmic expansion. A burst from a larger redshift is seen from an earlier epoch, and the path it traverses includes a longer stretch of expanding intergalactic medium. The dispersion measure must therefore be interpreted in a cosmological framework, rather than as a simple straight-line laboratory path. Contributions from the host side are also reduced in the observed frame by expansion effects, which is why the host term is often treated differently from the intergalactic term. These details do not weaken the method, they are part of what makes the method physically precise. The burst is not travelling through static space. It is crossing a universe whose scale changes over time, and the redshift of the host galaxy is the quantity that places the event within that larger setting. Once distance information enters the picture, the meaning of scatter also becomes clearer. If every sightline crossed a perfectly uniform medium, then bursts at the same redshift would show nearly identical extragalactic dispersion measures. They do not. Some lie above the average trend and some below it. This variation is expected because the cosmic web is structured. One burst may pass through a denser foreground halo or a richer filament. Another may travel through comparatively emptier regions. A host galaxy may also add more or less local plasma depending on where within that galaxy the burst originates. The observed spread around the average relation is therefore not an embarrassment to the method. It is evidence that the matter distribution is clumpy, filamentary, and environmentally varied. The mean relation reveals the broad census. The scatter reveals the uneven geography. This is why host galaxies matter in two different ways at once. First, they provide the spectrum from which redshift is measured. Second, they remind astronomers that not every electron counted by the burst belongs to the intergalactic medium. Some share belongs to the burst's local environment and host galaxy. A burst born in a dense star-forming region or within a highly magnetized and active local setting can carry an extra plasma contribution before it ever leaves its home system. That contribution must be treated as part of the full accounting. Yet even with this complication, the distance dispersion pairing remains powerful because the intergalactic share grows systematically with redshift across a sample. Local contributions create scatter and uncertainty. They do not erase the large-scale trend. The pairing of redshift and dispersion also changes how individual bursts are understood. A single burst with a high extragalactic dispersion measure, but no host may suggest a great distance, but the suggestion remains uncertain. A burst with both a secure host and a measured redshift becomes much more informative. Its observed dispersion measure can be partitioned into Milky Way foreground, probable halo contribution, intergalactic share, and host side allowance. No single partition is perfect, but the overall geometry of the problem is then fixed. Earth is at one end. A known galaxy at a measured redshift is at the other. The integrated electron count belongs to the space between, plus the local material at each end. In this way, localization and redshift measurement transform the burst from a free-floating clue into a bounded line of inquiry. Over time, as the number of localized FRBs grows, the relation between redshift and dispersion becomes more than a proof of concept. It becomes a working observational framework. New localized bursts can be placed against the growing population and compared with the average trend and its expected spread. Outliers can indicate unusual host environments, dense intervening structures, or especially long and rich paths through the web. More typical bursts reinforce the statistical relation. Each added host galaxy strengthens the bridge between radio timing and cosmological structure. What began as a curious fact about a few localized events develops into a general method for connecting invisible ionized matter with the known scale of the expanding universe. At this stage, the essential transition is complete. The burst is no longer only a signal with a swept arrival pattern, and it is no longer only a localized event with a host galaxy address. It is now a burst whose electron count can be compared with a measured cosmological distance. Delay meets redshift. Plasma content meets cosmic scale. The result is not yet the final census of missing ordinary matter, but it is the necessary step just before that census becomes possible. Once a burst has both a dispersion measure and a host galaxy redshift, the invisible matter between galaxies begins to move from suggestion to measurement, and the long path through the cosmic web can at last be placed onto the page of observation with both length and weight. With a localized fast radio burst in hand, and with its host galaxy redshift measured, the method becomes more than a way of detecting plasma. It becomes a way of weighing the long-missing share of ordinary matter itself. The central logic is simple. Cosmology already predicts how much ordinary matter the universe should contain in total. A localized FRB supplies an observed electron column along one real cosmic path. When many such paths are gathered, the average intergalactic electron content can be compared with the cosmic expectation. If the missing baryons truly reside in diffuse ionized gas spread through the large-scale structure, then the dispersion measures of localized FRBs should recover the required amount. Over the past few years, that is exactly what the data have shown. the method does not infer the missing matter from theory alone. It measures the ionized baryon content directly along sightlines and tests whether the cumulative total matches the long-established cosmic budget. The importance of this step lies in what older methods struggle to do. Emission studies can reveal hot gas where it is dense enough to glow. Absorption studies can find selected ions where a favourable background source happens to lie behind them. But neither method easily provides a broad, direct accounting of all ionized baryons along a random cosmological path. A localized FRB does. Its dispersion measure responds to free electrons wherever they are distributed, provided they sit along the burst's journey. This includes the diffuse gas that is too faint for ordinary imaging and too spread out for simple inventory by luminous tracers. In that sense, the FRB method is unusually democratic. It does not strongly prefer bright or compact structures. It counts the integrated electron content of the path, and ionized baryons that would otherwise remain observationally quiet still enter the total. That is why the method proves so powerful for the missing matter problem. The missing share is not mostly hidden in bright places. It is hidden in diffuse ionized space, and FRBs are sensitive to exactly that medium. The first decisive demonstration arrives in 2020, using a small but carefully localized sample of FRBs with known host galaxy redshifts. Astronomers show that the average dispersion-redshift relation agrees with the expected baryon content of the universe. This is a landmark moment because it changes the missing baryon problem from a persistent shortfall into a measured success. The data indicate that the ordinary matter predicted by cosmology is indeed present along the lines of sight, in the ionized form that the burst can trace. The result does not produce a detailed three-dimensional map of every baryon, but it does achieve something more fundamental. It closes the large-scale accounting gap. The ordinary matter budget implied by the early universe is recovered in the late universe through direct sightline measurements. What had been missing from conventional observational tallies is no longer missing from the baryon census as a whole. That early success is important, but it remains a beginning rather than an end point. A small sample can establish the method, yet larger samples are needed to reduce statistical uncertainty, average over unusual sightlines, and strengthen the link between the observed dispersion and the total cosmic baryon budget. In 2025, a much larger cosmological sample of localized FRBs sharpens the result considerably. With dozens of host-localized bursts spread across a wider range of distances, the census becomes more robust. The newer study confirms that the long-missing ordinary matter is not absent from the universe at all. It is present in the diffuse ionized component that FRBs are able to weigh. The larger sample also improves confidence that the result does not rest on a few exceptional paths. The missing baryons emerge from a population-level measurement across many bursts rather than from one or two particularly favourable cases. This is why the word census is so appropriate. A census is not merely the detection of a few examples. It is an accounting exercise aimed at the total. In the FRB case, each burst provides one line-of-sight electron tally after nearby Milky Way contributions are estimated, and after the host galaxy supplies a redshift. No single burst can by itself define the entire universe. But a collection of such bursts can be combined statistically to estimate the mean density of ionized baryons across cosmological space. Sightlines that pass through somewhat denser environments tend to lie above the average. Sightlines that traverse thinner regions tend to lie below it. The average over many bursts reveals the underlying baryon content. This makes the method especially well matched to a clumpy universe. The cosmic web does not need to be uniform for the census to succeed. It only needs to be sampled enough times that the hidden, ordinary matter of diffuse space appears in the mean. The result also clarifies the true nature of the old puzzle. The missing matter problem never means that cosmology fails to predict the baryon budget. It means that direct observational inventories of stars, gas in galaxies, and other familiar structures come up short. FRBs show that the shortfall is largely a problem of observational access, not a failure of the cosmic model. Once ionized plasma along long extragalactic paths is counted properly, the missing share reappears in the ledger. The universe has been carrying its expected ordinary matter all along. It is just not mostly stored in bright stellar bodies or other compact structures that are easy to tally. In that sense, FRBs do not discover a new substance. They restore a known substance to the books by measuring it in the state and environment where it had long been hardest to count. There is still uncertainty within the method, and that uncertainty is handled rather than ignored. Host galaxy contributions vary. Milky Way foreground subtraction is imperfect. Individual sightlines differ because the cosmic web is structured. The redshift dispersion relation therefore has scatter, and no honest analysis treats every burst as a perfect measure of the cosmic mean. Yet this is exactly why larger samples matter. Random variations and environmental differences become less dominant when many localized bursts are combined. The success of the FRB baryon census comes not from pretending that each path is simple, but from using enough paths that the broad average rises above the complications of any one of them. The method is statistical in its power and physical in its foundation. It rests on real electron columns measured along real journeys through the universe. By this point, the long arc of the argument becomes steady and clear. The early universe tells cosmologists how much ordinary matter should exist. The modern observational inventory of bright structures leaves a large share unaccounted for. Fast radio bursts cross the ionized cosmic web, and their frequency-dependent delays record the total free electron material along the way. Once those bursts are localized and matched to host galaxy redshifts, the delays can be compared with cosmological distance. Across a growing sample, the measurements recover the expected baryon content. The long missing share of ordinary matter is therefore not lost, exotic, or absent. It is measured through the cumulative plasma imprint on radio flashes from distant galaxies. The census closes not with a dramatic object entering view, but with a quiet accounting finally brought into balance. Finding the missing ordinary matter is one achievement. Learning where that matter resides is another. Once fast radio bursts begin to supply a growing sample of measured sightlines across the universe, the result is no longer only a recovery of the total baryon budget. It also becomes a way of sorting that budget by place. This matters because the old problem is not simply that a large share of ordinary matter fails to appear in visible inventories. It is that the material is distributed across several overlapping environments whose edges are not obvious in ordinary images. Galaxies contain stars, cold gas, and dust. Around galaxies lie broad halos of hotter, thinner gas extending far beyond the visible starlight. Beyond those halos lies the intergalactic medium itself, the vast plasma between galaxies, stretched along the large-scale web. For many years, simulations suggest that most of the missing baryons should live in the last of these regions, with a smaller but important share in halos, and only a modest remainder inside galaxies. Fast radio bursts now allow that expectation to be tested observationally, rather than left as a theoretical picture alone. The distinction between these regions is physical as much as geometric. Matter inside galaxies is the most familiar. It forms the stars that shine, the colder gas from which stars can form, the dust that dims and reddens light, and the denser structures that traditional astronomy has long traced. Halo gas is different. It is more extended, more diffuse, and often hotter. It belongs to galaxies gravitationally, yet much of it lies well outside the visible stellar body. The intergalactic medium is broader still. It fills the space between galaxies and groups, often in the form of a tenuous ionized plasma spread through filaments and lower density regions of the cosmic web. In an image, these three zones do not present themselves with neat dividing lines. But in the logic of the baryon census, the separation matters because each region tells a different story about how ordinary matter moves, heats, cools, and circulates through cosmic structure. The new FRB results show that the largest share of ordinary matter lies not in the bright interiors of galaxies and not mainly in the halos surrounding them, but in the intergalactic medium itself. The middle of cosmic space, long treated as visually empty, turns out to be the dominant reservoir of baryons. More than 3/4 of ordinary matter appears to reside in this thin medium between galaxies. Around 1/6 lies in galaxy halos. Only the small remainder is concentrated within galaxies themselves, in stars and colder galactic gas. This is a profound rearrangement of intuition. Human attention moves naturally toward galaxies because galaxies gather light into visible forms. Yet the baryon census shows that visible galactic bodies are not the main storehouses of ordinary matter. The great reservoir is the diffuse plasma spread through the web, while halos hold another important share in broad envelopes around galaxies, and the luminous material inside galaxies represents only the smallest part of the whole. This partitioning also clarifies why the missing baryon problem persists for so long. The hardest material to count turns out to be the material living in the regions least suited to ordinary observational methods. The intergalactic medium is vast and thin. Halo gas is extended and often faint. Both are more difficult to inventory than the stars and denser gas inside galaxies. Traditional surveys therefore give too much visual weight to the baryons in galaxies simply because those baryons are easier to see. Fast radio bursts do not remove this difficulty by making the gas glow. They remove it by measuring the free electrons integrated along long paths that cross all three environments. Once enough bursts are gathered, the statistical contribution of each region can be inferred. The census then reveals that what looks central in the sky is not central in the baryon budget. There's a calm physical logic behind this distribution. Galaxies do not keep all of their baryons tightly bound in their visible parts. Star formation, stellar winds, supernova explosions, and energetic activity around black holes can heat gas and drive it outward. Gravity also gathers matter into large-scale filaments and halos, rather than only into dense galactic interiors. Over cosmic time, ordinary matter flows inward, is processed inside galaxies, and is also pushed outward again into surrounding regions. The result is a circulating baryonic economy in which galaxies are important sites of transformation, but not the final resting place of most ordinary matter. Much of the material remains in the broader web or in the envelopes around galaxies, where it is ionized, tenuous, and hard to see directly. The FRB census fits this picture well. It suggests a universe in which baryons are not lost from structure, but redistributed through it. The halo share is especially revealing because it sits between the bright galaxy and the larger intergalactic medium. Halos are not simple leftovers. They are active reservoirs through which matter can pass on its way into galaxies or back out of them. A substantial halo fraction means that galaxies are not isolated islands with sharp edges. They are embedded systems with extended gaseous surroundings. The baryon census therefore softens the old image of galaxies as self-contained stellar machines. A galaxy is better understood as a dense centre within a much larger baryonic environment. Its visible body is only the inner part of a broader domain of ordinary matter. The relatively small share within galaxies also carries meaning. It does not diminish the importance of stars or cold galactic gas for astronomy. It places them in context. Stars are where chemistry becomes visible and long-lived structure becomes memorable, but they are not where most baryons spend most of cosmic time. The ordinary matter that builds stars is drawn from wider reservoirs, and much of it remains outside galaxies altogether. This is why the modern census feels at once surprising and natural. It is surprising to intuition, because intuition follows brightness. It is natural to physics, because large volumes of thin plasma can hold enormous mass while remaining dim. By sorting the baryons in this way, the FRB results do more than close a bookkeeping gap. They redraw the ordinary matter map of the late universe. The intergalactic medium emerges as the principal baryonic realm. Galaxy halos become major secondary reservoirs. Galaxies themselves remain luminous but minor in share. This is the deeper resolution of the missing matter problem. The universe has not hidden its ordinary matter in one overlooked object or one dramatic location. It has distributed that matter across a hierarchy of environments, with the quietest and most extended environments holding the greatest share. Fast radio bursts make that arrangement measurable. They show not only that the baryons are there, but also that most of them belong to the thin space between galaxies, with a further portion suspended around galactic systems, and only a modest fraction gathered into the bright structures that first teach observers where to look. At the innermost layer of this story, the fast radio burst is no longer treated mainly as a messenger crossing the cosmic web. It is treated as an event emerging from a particular local environment, and that environment can add its own plasma to the signal before the wider journey even begins. This is where the method becomes less clean and more human in its caution. A burst may arise inside a star-forming region, near a young neutron star, within a dense pocket of host galaxy gas, or inside a magnetized local nebula. All of these surroundings can contribute free electrons, and free electrons add to the dispersion measure in exactly the same broad way that intergalactic electrons do. The burst therefore carries not only the weight of the vast space between galaxies, but also the weight of the immediate material around its source. For most fast radio bursts, current evidence suggests that the host side contribution is often smaller than the intergalactic share. Yet, it is not negligible, and in some cases it can become exceptionally large. This local contribution is usually called the host contribution, though in practice it includes more than one layer. Some share can come from the general interstellar medium of the host galaxy. Some can come from the circumgalactic environment around that galaxy. Some can come from the burst's own immediate neighbourhood, perhaps very close to the engine itself. These layers are difficult to disentangle because the telescope measures their sum after cosmic expansion has already reshaped the signal. Recent statistical work on more than 100 well-localized fast radio bursts finds that host side dispersion measures are broadly distributed rather than fixed, with a log-normal-like distribution and a median value around 153 parsecs per cubic centimetre. The same study finds a moderate positive trend with redshift, but no statistically significant correlation with host stellar mass, star formation rate, or galaxy age. This means the local plasma term is real and important, yet not easily predicted from a host galaxy's broad visible properties alone. That uncertainty is one reason the most careful FRB cosmology remains sample-based, rather than dependent on any single burst. A host galaxy can look modest in ordinary light while still placing the burst in a locally dense plasma environment. Conversely, a larger or more actively star-forming galaxy does not guarantee an extreme host contribution for a specific source. Simulations also support this variability. They indicate that host galaxy dispersion depends on redshift, galaxy type, stellar mass, inclination, and the burst's projected offset within the galaxy. A burst seen through the thick plane of a spiral system can inherit far more host-side plasma than one launched from a cleaner outer region or from a different type of galaxy altogether. The host term is therefore not a single nuisance number to subtract once. It is a distribution shaped by geometry, galaxy structure, and local placement. A few sources show just how extreme the local environment can become. FRB2 019050B is the clearest warning. It is associated with a compact persistent radio source in a dwarf host galaxy, and has an estimated host galaxy dispersion measure of about 903 parsecs per cubic centimeter, nearly an order of magnitude above the average host contribution. In that case, the host side plasma appears to exceed the intergalactic contribution itself. The lesson is not that all FRBs are dominated by their home environments. The lesson is that some are, and that this fact makes blind distance estimates from dispersion measure alone unsafe. A burst with an unusually large local contribution can look farther away than it truly is if the host environment is not known. This is why accurate localization remains essential. Without a secure host galaxy, the burst's total delay can mislead as easily as it informs. The local environment also reveals itself through more than dispersion measure. Another quantity, called rotation measure, records how magnetized plasma rotates the polarization angle of the radio wave during travel, where dispersion measure responds to the total free electron column. Rotation measure responds to free electrons together with magnetic field direction and strength along the path. For this reason, rotation measure can become a sensitive indicator of dense, magnetized local surroundings. Some repeating FRBs show dramatic rotation measure changes over time, including oscillations, sign reversals, and abrupt jumps, while their dispersion measures change little or only stochastically. This pattern suggests that the immediate environment around at least some repeaters is dynamic, structured, and magnetically active rather than static and featureless. The burst is not merely leaving a quiet galaxy, it is crossing a living local plasma environment. Such behavior strengthens the case that at least part of the FRB population arises from compact engines embedded in complicated surroundings. Magnetars, which are highly magnetized neutron stars, remain among the leading source candidates, and the local plasma around them may include flare ejecta, nebula material, surrounding winds, or matter shaped by a binary companion. In some repeating sources, the evidence points toward a compact persistent radio source nearby and an extreme magneto-ionic environment, meaning a place where plasma and magnetic fields are both unusually strong. This does not prove that all FRBs are born in the same way. It does show that the local surroundings of some sources are capable of adding substantial and time-variable propagation effects. The closer the science moves to the burst itself, the less uniform the population appears. This is the innermost complication in the baryon story. On average, the intergalactic medium dominates the cosmological use of localized FRBs, and that is why the baryon census succeeds. But the method works statistically because individual bursts are not perfectly clean. Each one arrives with a personal history written into the signal by its immediate environment. Some paths start in relatively quiet host conditions, others begin inside denser, more magnetized, or more turbulent regions. Some repeaters evolve over time, showing that the local plasma is changing even while the source remains active. These source-side effects do not cancel the cosmological value of FRBs. They define its present precision limit. The broad average over many bursts recovers the missing ordinary matter, while the burst-to-burst differences remind astronomers that every line of sight begins inside a specific astrophysical home. So the final inward step ends very close to the source. The hidden baryons of the universe can be found because fast radio bursts cross the ionized web between galaxies, yet each burst also carries the imprint of the smaller place where it is born. Host galaxies contribute a variable share of the total electron column. Immediate source environments can add further plasma and strong magnetic structure. A few bursts live in especially extreme settings and warn against overconfidence. This is why the method is both powerful and careful. It succeeds not because every burst is simple, but because the larger intergalactic signal can still be recovered through many localized events, even while the innermost environments remain diverse, active, and only partly understood. The universe settles back into quiet scale. Between galaxies, the great reservoirs of ordinary matter remain thin, ionized, and nearly invisible, spread through filaments, halos, and wide intervals of deep space. Nothing in that broad arrangement appears hurried. The atoms do not gather only where starlight is strongest. Much of their long existence unfolds in diffuse plasma, suspended across distances so large that brightness falls away, and only patient measurement can follow their presence. A brief radio flash crosses that stillness, and in crossing it, carries the record of matter too faint to stand out on its own. The old absence softens into a different kind of understanding. The missing matter is not missing in substance. It is missing from easy sight. It resides in the quiet medium between the bright structures that first claim attention. The galaxies remain luminous islands, but they are not the whole coast of the cosmic sea. Around them and between them lies the larger share of ordinary material, dispersed, ionized, and real. The universe keeps its balance in places that do not glow strongly. Fast radio bursts appear and vanish in moments, yet their passage joins the largest scales to the smallest surroundings. A compact source in a distant galaxy releases a signal. That signal crosses local gas, galactic space, halos, filaments, and the long intergalactic medium. By the time it reaches Earth, its timing has become a quiet ledger of the journey. From that ledger, the scattered ordinary matter of the universe slowly returns to the page. So the story comes to rest not in a dramatic object, but in a calmer picture of cosmic order. The wide dark spaces are not empty. They are filled with thin matter, moving through the structure of the universe in forms that rarely shine, yet still shape the paths of light. The ledger closes. The missing share is found. The deep space between galaxies grows a little less silent and a little more known